thank you for coming this morning and for missing the last half of Car Talk. Let me first say, this is, as you know, this is the last of the Saturday science lectures for the spring, and I think we owe a great debt of gratitude to Michael Friedlander. I should say Michael is an absolutely wonderful asset to the St. Louis community because he has organized these lectures, and they have obviously turned out to be very popular. There's a great interest in science, and well, I think we all appreciate all the work that you've done. Thank you very much. Michael asked me a few months ago if I would take part in the spring lecture series, and I was trying to think of something that I could talk about. It wasn't that. Let me try to rearrange. There, that's better. We just a mere rearrangement of the letters. So I tried to think of something that wouldn't require too much time for me to prepare it. Normally, of course, if you prepare a lecture, you have to do a lot of reading and a lot of learning and that kind of thing. And I figured this would be very easy for me to prepare because nothing is known about it. So, in fact, it's a little bit like pornography. You know, it's very, very hard to define, but you know it when you see it. And I figured it would be about as easy as stirring a cup of tea. So let me give you some sort of introduction to the notion of turbulence. I should say that there have been lots of important breakthroughs in mathematics, and basically there are two things that go into turbulence. It's about mathematics and physics. Let me give you just a historical perspective. For example, one of the great breakthroughs in mathematics was the reduction of fractions to lowest terms. This is something that you normally teach in elementary school. That's how it's done. Okay. Those of you who know a little bit more mathematics know that this applies very easily to the solution of differential equations. This is a more advanced course that's taught to the undergraduates at WashU. Just to give you a clue, however, to how to solve a differential equation, you just cancel the d's and solve the algebraic equation. And that is the exact solution to the equation. I thought you would like that, Bob. I did this for you. And here's another example. It's a technique that was recently discovered. You see, you write down a true equation, like 1 divided by 0 is infinity, and then you rotate the equation 90 degrees anti-clockwise, like so. Okay? And that gives you minus 10 equals 8. And of course, you subtract 8 from both sides of the equation, which gives you minus 18 equals 0. But then you rotate back 90 degrees, and you conclude by 1 over infinity is equal to 0. One true statement leads to another true statement. It's purely rigorous. And one last example, how you derive addition theorems. If all you do is rearrange the letters in 1 plus 12, you get the letters 11 plus 2, so it must be a correct statement. Well, so much for mathematics. There are lots of important breakthroughs in science that I could talk to you about. For example, the real reason that the dinosaurs became extinct. Or the great discovery of classical gravity, which... but probably the most important discovery of this century was Einstein's discovery that time is actually money. Well, the problem with turbulence is that this is a problem that hasn't been understood at all, and it hasn't been solved. And I will describe it to you because it's an absolutely fascinating problem. It is one of the really, really big, not understood problems in physics. There's a lot of sort of approximate qualitative stuff that is understood, and I'm going to describe that to you mostly with words. But this is a discovery in mathematical physics that has yet to be made. And this is a problem that people have been working on for a very, very long time. When I was a professor at MIT, one of the people in the department, his name was C.C. Lin, very, very prominent applied mathematician, fluid mechanic. He was quite a strict guy, and he wasn't waiting for the final understanding of what turbulence is. He was rather, let's just say that he didn't expect it this century and probably next century, and he was so forceful about his opinions that any graduate student who submitted a thesis with the word turbulence in it, he failed them. Because he said, you've got a lot of gall to put the word turbulence in the title of your thesis if you have no idea what you're talking about. So the question is, what is turbulence? This is a picture of Mount St. Helens, and it is obvious that there's turbulence in that cloud, okay? It is obviously a very, very, very turbulent cloud. But the question is, what am I talking about? What is turbulence? Okay. So we have to go back to the guy who first coined the term. And the guy who first coined the term was Da Vinci. And he called it, he was the one who came up with the word turbulence. He called it turbulenza. Okay, and he was absolutely wonderful because he looked at natural processes in the world around him and he saw stuff that other people had seen for centuries but never noticed. Okay? For example, he looked at a stream and he noticed that there was a quiet stream flowing along, but there was another stream, an outpouring of water that was going into the stream, and this is his own sketch. And in fact, this is a really, really profound, really deep understanding of actually what was going on. What you see is that water was pouring into this stream, and it was creating eddies, okay, vortices. And you see those vortices, those curls of water, and what you see is that they're not just eddies or vortices, but there are vortices on all scales. There are big vortices, and there are small vortices. And turbulence has to do with the creation of vortices when fluid flows along. Okay? And he captured it in this sketch that he kept in his sketchbook. Okay? It's really remarkable. That is what turbulence is. And if we go back to this picture, now I can say a little bit more precisely what I mean by saying that there is turbulence here. The evidence that there's turbulence in this hot cloud of smoke coming out of the volcano, the evidence is that if you look at the smoke, it's not smooth. It's full of white bumps all over the place. There's a tremendous amount of internal structure in the cloud, and that structure is vortices. Okay, and that is basically, I mean, if you remember nothing else from today's lecture, it is that the difference between ordinary fluid flow and turbulent fluid flow is that in turbulent fluid flow there are vortices, not just vortices, but vortices on all scales. Okay? So basically, I'd like to begin by sort of, I guess maybe the best way to define something is to show you what it isn't. Okay? So let me show you, see, maybe we can get a piece of paper here. Yep. Let me give you an example of, let's turn this. Okay. Let me give you an example of fluid flow, which is not turbulent. Okay, and then we'll try to understand what is going on. Okay, let's see. Where's the hole here? Here it is. Okay, so let me describe to you what this is. I'm not a druggie, actually. This is hypodermic filled with a dye. Okay, it's a dark blue aniline dye, and this is a piece of plastic. It's two concentric cylinders, and the space between the inside cylinder and the outside cylinder is filled with glycerin, which is very viscous. And I'm making a little pattern here. Let me see if I can squeeze some more dye in here. Okay, now can you see that pattern of dye? Is it visible? Okay, now what I'm going to do is I'm going to stir this up. Okay, so what I'm going to do is rotate one of the two cylinders. Okay, now as I rotate it around, you notice that this is smearing out. In other words, I'm mixing the blue dye, and it's becoming quite mixed. In fact, I've rotated it a whole 360 degrees. Okay? Now, let me turn it backward. And as I go backward, okay, as I go backward, the original design in the dye returns, which is really amazing. Okay? This is not turbulent flow. This is laminar flow. Okay, so I'm showing you this to distinguish it from turbulent flow. In fact, let me mix it more. Let me go around once, turning it very, very smoothly. So there's once. And let me go around again. Twice. Okay? I've stirred it twice. Okay? Twice around. And now if I go backward, like this, so I've gone backward once. So it's again, the original mixture of dye is recovered. Okay? And in fact, I can go around many times. Okay? Here's once. Twice. 3 times. Okay? And if I go backward, there's once. And twice. And 3 times. So it's quite remarkable. So apparently, even though I've stirred up the mixture, the memory of the original pattern of dye that I put in that liquid is still there. Now, it isn't exactly there, okay, because there's a little bit of diffusion, but in fact, it's almost, I mean, if I had written my name in that, and I stirred it up 3 times and then unstirred it, you could read it. You could still read it, even though it's smeared out a little bit. And so this is an example of non-turbulent flow, that is laminar flow. And in order to make sure that this flow was very, very laminar, what we had to do was to use, this would not work with water because water is not viscous enough. So it works with glycerin, which is nice and thick and syrupy, very viscous, very slow flowing. Why do you want it to be viscous? Because you don't want turbulent eddies to appear. So what happens when you have turbulent eddies is that the system is no longer time reversal symmetric. Okay, so what does that mean? Well, Lord Kelvin thought about turbulence, thought very, very hard about turbulence, and he realized that turbulence does not have time reversal symmetry. That is, it cannot be run backward in time. Once you've stirred up a teacup in a turbulent fashion, you cannot unstir it. Okay? If you should move the thing in the backward, just move it backward, you certainly cannot unstir the sugar in a teacup. It's absolutely impossible. Okay? And Lord Kelvin called it vitiating rearrangement, which is really wonderful for something that he could have said much more simply, and that is that there is no memory. Okay? Basically, what you do when turbulence occurs, the memory of the initial conditions is lost. It's gone. Okay? And that's one of the features of turbulence. In this experiment, what I showed you was that the memory of the initial condition was not lost, and I was able to go backward in time by unstirring it. Let me see if I can show you a movie of something. Now, what you're looking at is this tube that's sitting right on the table here. And this tube, water is going to flow through the tube, and it is fed by this 8-foot-high glass reservoir. The water flows down from that reservoir and into this pipe over here, right over here. Okay? Furthermore, you see you see that bottle of stuff, that's a white dye. And that white dye flows in through this pipe over here. So you can see there's a beaker of dye that's flowing into this tube. Okay, do you all see this now? So now what's going to happen is that we're going to put water in through this entry point. Then water is just going to flow out into the sink on the other side. Okay, and what we're going to do is gradually increase the speed of the flow. Okay, so you see that little point on the left. That little point on the left is the nozzle right over here where the dye is going to come out. Now, this is very streaky, but we've just turned off the lights in the room. Okay, so now you don't see any more reflections from the lights. But that white point on the left is where the dye is going to come out. Okay, so there's the dye coming out into the water. And you notice that it flows along in a laminar fashion, but eventually it begins to swirl around. Okay, so after it flows in a laminar fashion for a while, in a smooth laminar fashion, it begins to develop eddies. Okay, now what is happening, what we're going to do now is gradually speed up the flow of the water. Look at the white streak of the dye. The white streak of the dye so far is flowing along very, very, very smoothly. So at this point, the flow is laminar. But do you notice that as we speed it up, waves begin to develop? You see the waves in the dye gradually developing? And the waves, as the speed increases more, the waves begin to break. Do you notice that? The waves are breaking. And now the dye is not just flowing down the center of the tube, but it's actually reaching both sides of the tube as we speed up the water. So turbulence is developing, and it's mixing the dye into the water. And because it's mixing the dye in the water, all of the initial conditions, it's like stirring up a teacup, the initial conditions are gone, and it's impossible to unstir this. Okay, now what's going to happen at the end of the film is that we're going to slow down the speed of the water, and once more, the laminar flow is going to be reestablished, which is really interesting. So you notice now, as we slow down the speed of the water, once again the dye is flowing very smoothly all the way across to the end of the tube. So the turbulence is gone now. The dye is no longer mixing in the water. And now this is very much like the glycerin experiment I just showed you. Okay? Now we're going to speed it up a little bit. And again, waves are developing. And the waves break, and once again, vortices are formed. Okay? So you can turn the turbulence on and off, and you see these beautiful vortices developing. You notice the way they're spinning? Can you see them spinning? should turn this. Okay. Let's see if we can. Okay, and again, here we're slowing down the fluid. The turbulence is gone, or is almost gone. Okay? You notice that all the way at the end, some waves are beginning to develop, but most of the turbulence is gone. Okay, so that gives you a feeling about turbulent flow. Basically, there is a you know, if you take a course in fluid mechanics, the way turbulence is usually described. By the way, I should give credit. That movie was made by Stan Krohn, who is the guy who organizes our experiments and who's absolutely wonderful. He's been here for many, many years, and he's designed some absolutely wonderful, wonderful experiments that we use when we teach our classes. This was an experiment that Stan developed for Jim Miller's class that he teaches. Jim is an excellent teacher here, and was giving a lecture on turbulence. If you go to a lecture on turbulence, this is usually the simplest way that people describe it. Suppose you have a flat plate, and here is a fluid that's flowing along the flat plate. So just some water is flowing along the flat plate. What happens? Well, if the flat plate were absolutely slippery, so slippery that the water did not even know that the flat plate was there, if the water was just flowing along slowly, you would have a stream of water where everywhere where the flow was very, very smooth, very laminar. And what laminar really means is that if you indicate the amount of velocity in the water by the length of the arrow, that is, the faster water has a longer arrow, you notice that the velocity here is almost constant. The water is flowing along very smoothly. This atom of water is flowing just as fast as that atom of water. Okay? But this is not, in fact, the case. It is not true that if water is flowing across a flat plate, that the flat plate is absolutely slippery. In fact, the molecules that are actually touching this plate won't slip at all. In fact, people who do fluid mechanics call this the no-slip condition. And that's a scientific terminology. So that's what it's called. And so, in fact, what happens is this. The water that is actually in contact with the plate is really not moving. It's only the water that moves away from the plate that is moving. And if you draw a velocity profile, the velocity profile looks like this. The velocity of the water out in the free stream is basically uniform. But as the water gets very close to the plate, it begins to slow down. Okay, so here the water is going slower, here the water is going still slower, still slower, still slower. And in fact, by the time it gets to the plate, it's not moving at all. So the velocity profile of the water looks something like this. It's roughly constant midstream, but as it approaches the plate, it's not flowing very fast. And this is intuitive, you understand that. This region is called a boundary layer. It's the region in which the profile, the velocity profile of the water, is changing very, very rapidly. Okay? Now, this boundary layer has a thickness, and it's very, very thin. Typically, it's maybe only a few millimeters or at most a centimeter. Okay? But as the water flows down the plate, something very interesting happens to the thickness of this boundary layer. What happens is that the boundary layer begins to develop waves. That is, the thickness of the boundary layer, it gets a little bit thinner here, a little bit thicker, and a little bit thinner, and a little bit thicker, and a little bit thinner, like this. And what happens is, as the water continues to flow along the plate, these waves become bigger. And eventually, these waves break off. Okay? These waves become very thick, and they begin to break, like that. And this leads to chunks of water that go spinning off into the solution. Okay? that is the formation of eddies. And this is called the transition to turbulence, because initially, back here, the water flow is quite laminar, quite smooth, okay? And you don't see any kind of eddies. And later on, these eddies begin spinning off into the stream. And of course, I'm not as good an artist as Da Vinci. He really captured it in his drawing, okay? And it's really quite remarkable. So there is a transition from laminar flow to turbulent flow. Now, this transition is a very quick transition if the water is not very viscous, that is, not very syrupy. And the transition is a very slow transition if the water is, or if the liquid is very thick, very viscous. Okay? So, so I recommend, this is an intellectual Saturday morning science talk, I recommend that you see a play. The play is Arcadia. Tom Stoppard wrote this play back in '93. It's an absolutely wonderful play, and I strongly recommend it. The way it's normally presented is that it's given in 2 acts. And it's a play about the relationship between the past and the present, and order and disorder, certainty and uncertainty of knowledge. And if you listen very carefully to the play, you could tell that Stoppard must have gone to a cocktail party of physicists. And he was listening to these physicists chatting about things, and they were talking about the uncertainty principle in quantum mechanics, which has to do with loss of knowledge. And they were also talking about chaos in classical mechanics, which also has to do about loss of knowledge, loss of memory, vitiating rearrangement. Okay? It's the kind of loss of memory that in that experiment there we didn't have. Okay? Well, the first half of the play is about chaos, how information is lost, knowledge is lost when you have disorder in the system. And turbulence is about disorder. It's clearly about disorder that occurs in fluid flow. And in quantum mechanics, there's also a loss of information, and that loss of information is expressed in the Heisenberg uncertainty principle. So there are 2 kinds of sort of loss of information that occur, one at the classical level. This turbulence, what we're talking about today, is really purely classical physics. We're talking about the solution of Newton's equations applied to a fluid, and these are equations that have been known for centuries, okay, and we still don't understand them. But it is clear that these equations give rise to chaotic flow, which has to do with loss of information and irreversibility of time. That is, we cannot go backward in time. Okay, quantum mechanics is a 20th century theory, and surprisingly, it also involves a loss of information. And there are many relationships between classical and quantum mechanics. In fact, if you behave yourself, maybe I'll show you some pictures taken from a paper I submitted less than 24 hours ago about that relationship. But maybe you won't behave, and maybe that's the better choice. In any case, turbulence is very interesting because it's very good at transporting things, absorbing energy. For example, in this crowded room, if somebody is wearing perfume, almost everybody will begin to smell it. And if somebody has measles, almost everybody will be exposed. Okay? And this will happen very, very quickly. Now, if you were wearing perfume and the air in this room, if the air in the room was completely dead, that is, there were no vortices, the perfume that this person was wearing would have to spread, and it would have to spread just by diffusion. Diffusion is an extremely slow process. You wouldn't smell smoke or perfume for years, literally years. It spreads at the rate of millimeters, okay, every time unit, every minute or 2. Okay, so it's a very, very slow spread. But in fact, the air in this room is very turbulent. And because there are turbulent vortices, these vortices can pick the perfume or the viruses or the smoke, pick it up and carry it around the room very, very, very efficiently. So turbulent fluid is very good at transporting things, transporting chemicals, odors, for example, also energy. So when an airplane is flying through air, what you want to try to do is reduce the amount of turbulence. In fact, many of you have noticed, if you fly a lot, you notice that the end of a wing, the wing tends to curve up. There's a little piece that's been added to many airplanes where the tip of the wing curves up. The objective there is to reduce the amount of turbulence, because turbulence carries away energy, and as a result it produces drag. Okay, so airplanes would like to fly in a laminar fashion, not in a turbulent fashion. Okay, and I have a beautiful experiment. I hope it works. It's my sewer pipe experiment. Some of you may have seen this before. I really love this experiment. Let's see if okay. So this is an almost empty sewer pipe. So I will show it to you. You can look up the pipe. There's nothing up my sleeve. Okay. However, if you look in this side, you will see that there's some obstruction in the pipe. Okay. All there is a wire screen, the kind of screen that a chemist uses underneath, that a chemist puts above a Bunsen burner to spread the heat of the flame from the Bunsen burner. So there's just a wire grid, and it's held into place by these screws over here. The name of this is a Reiki tube. Reiki. I think more properly it would be Reiki, but I'm going to say Reiki tube because... So this is nothing but a sewer pipe, and what I'm going to try to do is to use this torch to heat up the wire. Now once the wire is hot, there are exactly two ways in which I could hold this tube that would be interesting. One way is like this. And what's going to happen is that if I have a hot wire in the tube, it will heat up the air in the tube, and the air in the tube will rise, and the tube will just be a chimney. Okay, it's perfectly straightforward and simple. Okay, or I could hold the tube this way. And again, here is the hot wire. It'll heat up the air in the tube. The hot air will rise, and it will become a chimney. Doesn't seem very different. However, do you remember that I explained to you that when fluid is flowing across a flat plate, it eventually begins to develop vortices? Now, if I hold the tube this way so that the hot wire is near the top of the tube, the airflow in the tube will remain laminar until it goes out the top of the tube and nothing will happen. Okay? But if I hold the tube this way, what we hope will happen is that the air in the tube, as it rises up this tube, will gradually become more and more turbulent, and there will be eddies of all sizes created in the tube, all sizes. Okay? And these eddies, some of them will be large, some of them will be small, but they will eventually interact. They're energetic, they're carrying a lot of heat energy away, they are energetic, and they will drive the natural frequency of the tube. And hopefully, you'll hear it. Okay. Whoops. Okay, so let me heat up the wire in the tube. So now it's beginning to glow red hot. And it continues to glow until the air has cooled it off. And what you see here is a direct conversion from heat energy into sound energy. But now I want to show you what happens when I turn the tube upside down and turn off the turbulent flow. Okay, let's see what happens now. Okay, it stopped instantly, and that's because the tube stopped acting like a generator of turbulent flow, and instantly there was laminar flow. Because there were no more vortices, I was no longer driving the tube to resonate, and so it shut down. Okay, so when I hold the tube like this, it's just a chimney, but it's not a resonator. Okay, show you one more time. Okay, so that's a very, very graphic demonstration of how turbulent flow is capable. Turbulent flow consists of vortices, and these vortices are highly energetic, and they are carrying the heat energy away from this hot grid of wire and actually driving the tube into resonance. Okay, and what you heard was the natural frequency of the tube. In fact, this is how you make a foghorn. Okay, no moving parts. Direct conversion of heat energy into sound energy. Okay, well, there is a really fancy equation that I would like to show you. So far, I haven't said anything about equations, but I want to show you one equation. And this is the equation. This equation is called the logistic equation, and I want to say a little bit, for those of you who like more quantitative discussions, I want to say a little bit about what turbulence is at a mathematical level. When I say at a mathematical level, I'm going to be speaking to you at about the level of 9th grade or maybe 10th grade in high school. So you all know, I hope, what a parabola is. A parabola is a curve that looks like this or like this. Okay, you know that. In fact, you know that if you throw a baseball, if you're over here and you hit a baseball, the baseball will go in a curve, go up here and across and down. It'll follow a parabola. In case you have trouble remembering that, all you have to remember is a mnemonic, which goes okay, now you'll remember it. A lob, a rap as bat stabs, a parabola. The way you can remember this is that, you see, it reads backwards as well as forward. It's So you know roughly what a parabola is. In fact, if you make a graph of the curve x times 1 minus x, that is an upside down parabola. Okay? And to see that, here is the x-axis, and here is the y-axis. Okay? And it is obvious that at x equals 0, y is equal to 0. And at x equals 1, y is equal to 0. Okay? And in between, this is positive, so it comes up like this, and it comes back down. Okay? And that's an equation for a parabola. Now you can ask, how high is that? Okay? What is the height that it goes to? And this parabola is symmetric. So at the point 1/2, it reaches its maximum. And if you put in x equals 1/2, this is 1/2 times 1 minus 1/2, which is 1/2. So the height of this parabola is 1/4, which is a silly number. So I'm going to multiply this by 4. So now the height of this will be 1. Okay? So that is roughly what the curve looks like. And the height of this is 1. And in fact, if I didn't want it to be 1, if I wanted the height of this parabola to be something other than 1, that's okay too. All I have to multiply by is some other number. And I'll just call this number a. Okay? Some other number, a. And now, if I make a plot, instead of rising to the height 1, since I've multiplied by a, it will rise to the height a. Okay? So this curve looks something like this. So here's x. Here's 1. And I'm going to make a box, okay, whose size is 1. Okay? And I'm going to plot y here. And what the parabola looks like is roughly like that. Okay? I'm not much of an artist, but hopefully that looks good. And the height of this is exactly a. So we've plotted that curve. And this is the kind of thing you do in high school, I guess. Turns out this is a really, really interesting equation for the following reason. Suppose I take, let's explain it this way. Suppose I take a point, x, over here, any value of x, and I ask what is y. All you have to do is draw a vertical line until it reaches the curve, and that is the value of y. You all understand that, right? But now I'm going to do something very interesting. I'm going to take that value of y and put it back into this. I'm going to call that value of y x. And I'm going to do this process again. So in other words, I'm going to take a number x, and I'm going to find the value y. And then I'm going to take the resulting value y, put it back into the equation, call it x, and calculate a new value of y. And then I'm going to use that value of y to calculate a new value of y. And I'm going to continue this process over and over and over again. Now you might wonder, why is this interesting? It's not obvious why this is interesting. Okay. Now, of course, I didn't bring a pocket calculator along, and so doing this is a rather complicated and difficult thing to do. Because if I took a value of x on my pocket calculator, if x was 0.19, then I'd have to calculate 0.19, okay, times 0.81, multiply that by 4, multiply it by whatever the number a is. I haven't told you what a is, it doesn't matter. And then I get a number. Then I do it again and again. This is really boring, very, very boring. So I'm going to show you a trick. And the trick is this. Okay, and this is the only place where you have to concentrate. It'll be over in a minute, so the pain. In fact, I'm proposing to give you this explanation under a local rather than a general, so that after it's overword, you'll be able to hear the rest of the talk. But so I'm going to draw a diagonal. Okay, here is the diagonal. This is a square whose sides are 1, and I'm going to draw the diagonal. Now, you know from high school geometry that if you draw a line like this, it will be the same length as a line like this. Okay, you know this. Perpendicular bisectors, angle bisectors, stuff, something like that. Okay, now, suppose we want to do what I suggested. Suppose we want to take the number y that we get and use it for the new x. Okay? So I want to use the number y that I've gotten, use it for the new x. How do I do that? Well, for example, here is a value of x. I go up to the curve, and I find my value of y, the length of this from here to here. The length of this line, that is y. Now, let me go, I want to find out where is the new x. But it's easy, okay? Because if I go sideways here, until I reach my diagonal line, do you agree that the length of the line from here to here is the same as the length of the line from here to here? You agree, right? But the length of the line from here to here is y. And the length of the line from here to here is the same. Therefore, the length of this line from here to here is y. So, here's the game. Let me repeat it. We start with a number x. We go up until we hit the curve. We go across until we hit the diagonal line. And then we go back down to the axis. And the distance from here to here will be that value of y. So just by drawing a picture, I don't have to use my pocket calculator. Okay? So here is my new value of y, right there. Now I can repeat the process. Okay? I can go all the way up to the curve, across to the diagonal line, down to the axis, and this is my new value of y. So I go up, across, and down. That's my new value of y. And just by drawing pictures, I can iterate this equation over and over and over. Okay, did you follow that? Okay, the local is wearing off now. That's all. Okay, so now let me draw some pictures. Because I think you'll find that what happens is quite interesting. Okay, so this is supposed to be a square. It isn't quite, but that's okay. There is my diagonal. And I'm going to take a value of a which is small. Not 1, maybe about a quarter or something like that. So if a is a quarter, maybe 0.2, a fifth, something like that, if you ask what will the parabola look like, the height of the parabola will be a. Okay, so if I take a to be a quarter, the height of the parabola will be a quarter. So it will be somewhere like this. Okay, and the parabola will be a very low parabola. Okay, now let's see what happens if I repeat this process over and over. Well, let's start with this value of x. Doesn't matter which value of x, but we could start with this value of x. And let's play the game that we just made up the rules for. So we go up to the curve, across to the diagonal, horizontally, and back down to the axis. So if that's my first x, here's my second x. Now, I play it again. I go up to the curve, across to the diagonal, down again. That's my third x. I now go up to the curve, across to the diagonal, down again. That's my fourth x. Do you see what's happening? If I continue this process, up to the curve, across, down again, up to the curve, down again, it looks as if I have converged to 0. So it doesn't matter, in fact, what number I start with, any number here. If I do this process over and over and over again, I converge to 0. Okay? So now let's take a little bit bigger. Okay? Okay, so instead of taking a to be a quarter, maybe we'll take it to be, say, we'll make the parabola come up about that high, say. Maybe even, well, about that high. Let's take it to be that high. And let's see what happens. Well, if I draw the parabola, it looks something like this. All right? And let's take some initial point, it doesn't matter which, say a point over here. We go up to the curve, across to the diagonal, down again. So this is my first x, that's my second x, up to the curve, across to the diagonal and down again. That's my next x. Up to the curve, cross to the diagonal, down again. Okay, up to the curve, cross, down again. And in fact, I'm converging right over there. This is really very interesting. Instead of converging to the point at 0, I am now converging to a point in the middle. This is really very interesting. In fact, there has been a changeover. Okay? A physicist would call that a critical point. We passed a critical point, and now this system is behaving differently. Instead of just these points converging to 0, it converges to a point in the middle. Okay, well now I'm going to show you one last picture. I'm going to show you something remarkable. If I can draw it well enough. You may not be able to see it unless I can draw it well enough. Let's take this about here. Okay, here's my square. This is 1. This is 0. There's my diagonal line. Okay? And let's take a even bigger. Okay? So maybe we'll take A up around here. All the way up there. So A is about 4/5, 0.8, maybe 0.85, something like that. We draw our parabola. Okay, looks roughly like that. And let's take some initial value of x. Say, here is my x1. And let's play the game again. x1. We go up to the curve, right? We go across to the diagonal and down again. Up to the curve, across to the diagonal and down again. So this is x2, this is x3. And let's keep playing. Up to the curve, across to the diagonal, down again. Up to the curve, cross to the diagonal, down again. Up to the curve, cross to the diagonal, down again. And in fact, what I end up with is a picture like this. It keeps going around and around and around. In fact, it has no longer converged to a point, but it has converged to an orbit. Okay? So it is jumping back and forth between these points. It goes up to here, cross, down again, up to here, cross, down again, here, down. And it's going around and around like this. So it is no longer converging to a point. It is converging to an orbit. And this reminds me a little bit of a vortex. Okay? In fact, at this point, my artistic talent runs out. You have to really do this with a ruler and a straight edge, which I'm not going to do. But if you take a even bigger, what you'll find is that it doesn't converge just to a 2-cycle, jumping back and forth between those two numbers, but in fact it converges to a 4-cycle, jumping back and forth between 4 numbers. An even more powerful cycle, okay, longer, more powerful cycle. And in fact, if you continue this process, taking A bigger and bigger and bigger, the cycle gets longer and longer and longer. So this cycle here, this is only a 2-cycle, but we get a 4-cycle, and then an 8-cycle, and then a 16-cycle. It's quite remarkable. That's why this equation has the name logistic equation. It sounds like it's interesting. Okay? And eventually, and so the cycles get longer and longer and longer. However, it's really very, very hard to pick the A's. And the reason is this. Each subsequent A differs from, so the A where you get a 1-cycle over here, this A, you have to make it bigger to get an A for the 2-cycle, and you have to make that even bigger to get the A for the 3-cycle, and even bigger to get the A for the 4-cycle. The differences between these A's get smaller and smaller. That is, the distance from this A to this A is some small number, maybe on the order of 0.1. But the distance from this A to this A is about a quarter as much, and the distance to the next A is about a quarter as much. So the A's are getting closer and closer and closer together. But it isn't exactly a quarter as much. In fact, it's 1 over, not 1 over 4, not a quarter, but 1 over 4.6692016091029906718 and so on. That is the number, that is the distance between these A's, okay? And this is apparently a new fundamental number in mathematics, like pi, like the natural log of the base of natural logarithms, e, okay, which are transcendental numbers. Nobody knows what that number is. That number might be 3/2 pi, but it isn't. People have tried it. Okay? Of course, it would be absolutely fantastic if somebody who was playing with their pocket calculator managed to figure out how to express that number in terms of some other number, but so far no one's been able to do it. It appears to be an entirely new number, and what this number represents is the approach to turbulence. You remember I talked about this approach to turbulence. Do you remember I said to you that as fluid flows across a flat plate, it gradually becomes more and more and more turbulent until finally it reaches a stage of turbulence. Okay? Well, if you take these A's, this sequence of A's, until you reach A infinity, at that point, what you get is a cycle that's not a 2-cycle or a 4-cycle or an 8-cycle or a 16-cycle. It's a cycle that is infinitely long. And that is the transition to turbulence, okay? At least on a very, very, this is of course a model, and it's a very, very idealized model, but it is a mathematical model showing the transition to turbulence, which is very, very subtle. And in fact, it is a transition to chaos where at that point, none of the initial conditions can ever be recovered. So I thought I would show you a chaotic system here. So you see what this is. This is just a pendulum, except it's not a simple pendulum where just one thing is rocking back and forth as in a grandfather clock, but it's a pendulum with a tail on it. It's a double pendulum. It's called a complex pendulum. And if you let it go, you have to make sure it doesn't bonk you in the head. If you look at it, it's absolutely impossible to predict what's going to happen next. This is actually a very, very complicated system. And it is behaving in a totally chaotic fashion. And it's a remarkably simple system, and yet it really, really exhibits chaos. It is unpredictable, and it is impossible. The equations of this are easy to write down, but the solution is obviously very, very, very complicated. And that's because it really is a chaotic system. So what you see here is a transition to chaos. Turbulence is clearly an example in fluid motion of a chaotic system where things are happening apparently randomly and unpredictably. Okay, well, I thought I would show you, before I quit, something that I did with a student of mine whose name was Jade Vinson. It still is Jade Vinson, actually. It's a very, very smart undergraduate student. And Jade, for this bit of research that Jade and I did, this turned out to be very good for Jade. Jade won the prize that is given out by the American Mathematical Society and the Society for Industrial and Applied Mathematics. He won the prize for the best undergraduate research in the country. And I thought I would show you what we did. If you look on the left side of that equation, you see a very rather pretty picture. This is called the continued exponential. So you can put, if you have your pocket calculator, you can push the exponentiate button, EXP, which is the opposite of logarithm. And you can then multiply by a number z, and then push the EXP button again, and multiply by the number z, and push the EXP button again, and multiply by the number z. And you can do this over and over and over again, which is a little bit reminiscent of this logistic equation I showed you, where we do something over and over and over again, and you can ask what happens. And never mind the equation on the right-hand side. That's a Taylor series, and for those of you who know what a Taylor series is, you will recognize it. You can ask, if you continue this process, does it converge or not? That is, does it converge to a point like this, or a point like this, or does it converge to a cycle? Well, what we discovered was everywhere inside of that, you see that heart-shaped region? This is the complex numbers. This is the complex plane, and that heart-shaped region in the complex numbers, everywhere inside of that heart-shaped region, this continued exponential converges to a limit, to numbers, okay, just to a number, okay? So you start with any complex number inside of that region, and it converges to a number. If you repeat the process over and over and over, it approaches a point, just like this. But the question is, what happens out of that region? And this is the picture. This is an absolutely beautiful picture, one of the nicest pictures that I have published. This is a picture of what happens outside the region. Now, I have to describe to you what is going on here. Do you see this purplish heart over here? You see this purplish heart-shaped region lying on the side? Okay. Well, this is half of that heart-shaped region. Okay, the other half comes around like this and comes back. That was the region where the numbers converge. But outside of this heart-shaped region, the number, if you start with a number, this is useful. If you start with a number inside of this region and you run that continued exponential over and over and over, it converges to a point just the way this converges to a point right over there. But outside of the region, remarkable things happen. For example, in this red region over here, if you start with a number in that red region and you run the process over and over and over, it converges to a two-cycle. That is, it converges to a picture just like this. Okay? So you start with a number and you run that, you exponentiate, you keep pushing the button on your pocket calculator over and over and over, many, many times, and it eventually converges to two numbers, and it oscillates back and forth between those numbers. In this region here, it converges to a three-cycle, and in this region a four-cycle, and in that region a five-cycle. And in fact, we went all the way up. We found 2 cycles, 3 cycles, 4 cycles, 5 cycles, all the way up to about 15 cycles, which is the point at which his computer was running out of memory and running out of time. To draw this picture, it took about a month of computer time. And what we did was to take every single pixel on the computer and allow the computer to run it millions of times until we could be sure what kind of cycle it approached. Okay? What is quite remarkable and what is really beautiful about this picture is that each of these regions here, you see that each region seems to end in a little crescent here. You see the little crescent? The region doesn't end there. That was the point where his computer could no longer compute. It required too much computer time. But in fact, each of these regions continues on. Each region looks like a tadpole with an infinitely long tail. It's absolutely beautiful. So each of these regions continues on like this, and it becomes thinner and thinner and thinner and runs all the way off to infinity. In fact, every single region is shaped like a tadpole. So for example, this little region in here, you see there's a little crescent. You can't really see it, but it ends at this point. It seems to end at this point, but it doesn't. It's just that its tail is getting thinner and thinner and thinner, and its tail finds its way out through here, comes around like this, and runs off to infinity. Okay? So every single region has an infinitely long tail that becomes thinner and thinner and thinner as you go off to the right. So you have, if you can imagine, an infinite number of train tracks all running off to the right, coming from every single one of these tiny regions. In particular, so take this little purplish region here. Its tail runs out through this hole, it sneaks out through here, and it runs off to infinity. Okay? So what we have here is, apparently there's a process that's really very, very, very natural and very interesting, and suggests, so what you see here is obviously something you may have heard the word fractal. This is a fractal structure. And chaos and fractals are deeply connected, and underlying all of this is the nature of turbulence, which seems to be a fundamental and universal property. That number I showed you, that number, that long number, is apparently a fundamental number, and it applies to all processes. It is actually a universal number, and it is as universal as pi. Turbulence occurs everywhere in nature, not just in these simple mathematical models, but it occurs in all sorts of fluid models. It occurs in air and water and so on. And the approach to turbulence is a deep and fundamental thing. And although there are lots of results, as I said at the beginning of this lecture, nobody understands it at all. Okay. I thought I would just end with one remark. Okay. And that is this. I just published a paper, kind of proud of it. Got it done yesterday afternoon. We worked very hard all week writing this damn paper. So what we discovered, and we're really kind of pleased about this, you remember I began the talk by talking about Tom Stoppard's play, Arcadia, which is a wonderful play, and again, I strongly recommend you see it if you have the chance, or read it. The first half of the play is about classical chaos, but there's something I didn't talk about in the lecture, and that is quantum uncertainty. Chaos is associated with uncertainty, with unpredictability. And quantum mechanics is also connected with uncertainty. And what is remarkable is that, although this is two different kinds of uncertainty and unpredictability, in fact, these things are much more alike than you would think. Now, in fact, Einstein didn't want to believe in quantum mechanics. He said quantum mechanics must be like classical mechanics, except there must be a hidden variable. Well, we think that we have understood, at least in part, where the hidden variable is, and it has to do with the complex numbers. So you know that there are not just real numbers, but there are complex numbers. And if you study classical mechanics in the complex plane, okay, that is, if you allow the particle to move in the complex plane, what is remarkable is that the particle actually behaves like a quantum particle and not like a classical particle anymore. So what does this mean? So I will tell you in just 3 minutes what this means, and then I'll stop. If you have a particle on a spring, you have a spring, okay, and you attach a particle to it, and you stretch the spring out, the particle bounces back and forth. Okay, you know this. So when we study this in first year physics, undergraduate physics, we say this. Here is x equals 0, and you pull a spring all the way out, and you let the particle go. It bounces back and forth. And we have a fancy word for that motion. It's called simple harmonic motion. Okay, it's an oscillator. Okay, and this is all we study, just that much. And if you give a particle this much a certain amount of energy, this is as far as it can go. With the energy that it has, it can only stretch the spring out that far and not further. So after you give your lecture, a very, very bright undergraduate student might come up to you. So far it hasn't happened to me, but maybe they would. And the undergraduate student might say, what happens if you start the particle over here? Well, you know, we're really nasty to our students. We say, you stupid undergraduate student, you don't know what you're talking about. Particle can't be over here because it doesn't have enough energy to get there. But the student is insistent. And the student says, what if you start the particle over there? Okay, so you go back to your office and you think about it very hard. And you realize that what the particle really is going to do is to travel in the complex plane. And what it does is it travels like this in the complex plane, and it actually makes an ellipse. And in fact, no matter where you start the particle motion is always an ellipse. It's a little bit like the orbit of a planet, except it's moving not in real space, but in complex space. And in fact, this back and forth motion is not really back and forth. It's really a degenerate ellipse, which is something that people have not understood. It's really making a very, very tiny ellipse like that. Okay, so in fact, that's classical mechanics in the complex plane. But now I'm going to put in one more ingredient. There is, and I've talked about this in public before, there is a very, very famous principle called the uncertainty principle. And the uncertainty principle says that when we perform an observation, we can't measure everything exactly. One example of the uncertainty principle is that if you have only a finite amount of time and you measure an energy, okay, you can't measure the energy exactly, but there will always be a certain uncertainty in the energy. I didn't mean to say that. There will always be some uncertainty in the energy. And what we asked in this paper that I just wrote was, what if the uncertainty in the energy is complex, not just real? What if we don't know the amount of energy that a particle has exactly, if we have a certain lack of knowledge, and this lack of knowledge involves a complex motion? So what actually happens is that the particle does remarkable things. I will try to show you this. Here is a particle that is moving in the complex plane, and what it is doing is tunneling. This particle, instead of staying over here on the left or over here on the right, is actually tunneling back and forth. It is actually succeeding in tunneling. I want to see if I can show you. Yeah, let's try to show you this. Okay, so here is a particle moving in the complex plane, and this is a particle in a crystal. So we put this particle in a crystal, and it tunnels to the next site in the crystal. This is a classical particle doing something that you would never think a particle could do, that this only could happen in quantum mechanics. This particle is actually traveling in the complex plane and hopping, tunneling through the wall quantum mechanically, even though this is just a classical particle, and hopping from crystal site to crystal site. And I think this is absolutely amazing. Because this is just classical mechanics. This is, in some sense, what Einstein was looking for when he was proposing that there was a hidden variable theory. Because there is an uncertainty in the energy of the particle, that allows the particle to actually tunnel from site to site in a crystal. What happens to this particle is that it hops to the left and hops to the right and hops to the left, and in fact it appears to behave in a random fashion. Okay, now let me see if I can show you just one last picture. Let me see. Okay, this is a little faster. So here's a classical particle in a crystal that is actually managed. You see that it hopped to the left? Now it hopped to the left again. It's quite remarkable. It's apparent that classical particles can actually exhibit the same sort of chaos and same sort of uncertainty that you get in quantum particles. So maybe, if I can, I will show you just one or two movies, because you've behaved yourselves, just so you remember what turbulence actually looks like. I want to show you one or two very interesting movies that were sent to me by a friend of mine who studies turbulence. Yeah, this is a Dodge Ram truck, and you notice that the front left headlight air is flowing past the headlight, and you notice that it is beginning to develop eddies. It is then flowing past the rear view mirror on the outside of the car, the left mirror, okay? Turns out that they had a lot of trouble with the original design of this truck. The reason was it was very noisy in the cab of the truck. Why was it noisy? Because you see, there was turbulent flow that originated at this headlight, went past the mirror, and the mirror was hollow. And the noise came through the mirror into the cab of the truck, and you couldn't hear yourself talking. You couldn't hear the radio, for example. It was this analysis that led them to redesign, to reduce the noise, to redesign the plastic on the headlight. So it's quite remarkable. By changing this plastic on the headlight here and here, that reduces the noise in the truck. Okay? That was turbulent noise. Okay, now let me show you. This shows you the development of turbulent eddies as wind from a wind tunnel passes by a car. You notice this is very, very serious studies, because this shows you how to save gas, because this is a way of reducing drag on a car. Well, here's the last thing I'll show you. This is a hard drive on a computer. And as it spins many thousands of times per minute. As it spins, you can see turbulent eddies developing. Okay? That is the drag. That causes your wear and tear on the bearings that make your hard drive work. It's absolutely amazing. This actually shows you the development of turbulent eddies right in your own PC. Okay? It's quite remarkable. And you see these eddies spinning around here. All of these are turbulent eddies that are carrying away the energy from the computer and putting drag on the spinning wheel. If you're an engineer, that's what you have to get rid of to make it work right. Well, thanks for listening.